Today we're going to cover 10-3 and 10-4. So we're going to start just by taking our theta, alpha, and omega and relating them back to variables we're more familiar with, like position, speed, and acceleration. So to start with position, we could define position as the arc length S, and let me see if I can make this larger image. So when we're looking at the XY coordinate system here, then the arc length that this, let's say this object P has traveled would be S. If we know theta, then ooh, that's messy. Then we would say it's gone this distance in traveling the angle theta. But it might actually just be easier to find its position x comma y, because if you know theta, then, and you know r, I guess too, then you can find xy using right triangle trig. I think that would actually be more useful than finding S. So that's just my side note on that. But I mean, because theta is in radians, and radians is just a ratio, okay, then you can certainly find the arc length that's part of the circle that would be traveled eventually, if as this blob here is rotating. And, you know, point P on this blob is eventually going to rotate through the complete circle. But if you want to know what portion, you know, what far in distance, you can use that equation. When we look at speed, if you want to know speed, which would be tangent to the circle, or, you know, the direction is going to be tangent to the circle, and then the speed is going to be in meters per second, or, you know, kilometers per second, or feet per second, whatever. You would take the radians per second and just multiply by how far this point is from the axis of rotation. So, and on this example, you have like kind of like a maypole situation maybe, or for some reason there's this pole, it's attached to the axis of rotation here, and then you have like a bunch of people are all holding on at these different points, and which person is going to have to walk the fastest? Well, the person who is at the greatest distance, right, from the center of rotation. So you can see these velocity vectors have different lengths based on this r value here. But their angular velocity is all the same. That we already learned. Okay. And then we have to be a little bit careful when we talk about acceleration. So when something is on a rigid body and that object is rotating either faster and faster or slower and slower, so maybe if we're talking about the fidget spinner, when you first flick it, okay, while your finger is still touching the fidget spinner, the fidget spinner is accelerating. It has a acceleration alpha, okay, because you're getting it to go faster and faster. Or if you now, you know, let it spin, it is slowing down just because of friction. So there is a component of acceleration, right, in the linear, or sometimes it's called the tangential direction. That number can be calculated by taking the radius times alpha, if you would like to know what that is in meters per second squared or centimeters per second squared or something, okay? But you have to be cautious because there are two components of acceleration, because we already learned about one other one, and that was the centripetal acceleration for anything that moves in a circle, right? There is the center-seeking acceleration, and that is the AC. Sorry, I keep touching my screen. And I don't have my tablet today, so I'm struggling a little bit. Let's see if I can circle it. So this is the centripetal acceleration versus the tangential. So be careful, and I just have a slide on that to help us remember all these things. So we have the radial acceleration or centripetal. We've seen it referred both ways, okay? And that is anytime something's moving in a circle at a constant speed. That could be the car going around the, circular or semicircular curve. It doesn't have to be a rigid body rotating, and that's caused by some force that is pulling the object toward the center. So you would see this acceleration toward the center. And then there are also alpha and AT. Those are different. Those are accelerations that are caused by something else. And we haven't talked about what torque is yet. So we're going to get to that pretty soon. But those are accelerations that are happening. In the case of alpha, you're kind of measuring that in radians per second squared. And in AT, that's just meters per second squared, but it's explaining how a particular point on that rotating body, how fast that's going, like tangentially. Okay, how fast it's speeding up or slowing down in that direction. Okay, we're going to look at a simulation to try to put those two together, right? Because this is happening simultaneously. It's doing both. If you're talking about like a penny on like a record, on a record player or something. Okay. And then your book also points out that now that we know about what omega is, going back to centripetal acceleration, we have a new formula for AC, centripetal acceleration. So we used to always use v squared over r, but now we know the relationship that v is omega r. So then when you plug in omega r up here, then you can have this new formula. This is on your pink sheet. Notice now, like, AC is bigger when r is bigger instead of when r is smaller. Okay, so that means that if you've got an object, like a rigid body, like this, speaking of the penny on the record, or the record player, okay? Now if you know for sure that every penny on this record is spinning at the same omega, if you know that for sure, right? Because omega is the same for all these pennies, then you can say, okay, well, the centripetal acceleration is bigger when the penny is farther out, okay? That's different than like the situation of the car on a turn and saying that when R is bigger, AC is smaller. So that's why we were trying to be super careful with those types of questions in the circular motion chapter. You have to really pay attention to what is being held constant and what is changing. Okay, and then 10-4 is introducing the idea of rotational kinetic energy. That things that are, it's not just things that are like moving in a line that have kinetic energy, but also things that are spinning have kinetic energy. And there's this new concept that we're introduced to, okay, which is called rotational inertia or moment of inertia. And they derive this whole thing. But this quantity, capital I, which is, it has a formula for it, is really describing, does this object like to rotate or not? Okay, just like the quantity mass, m, is describing, does this object like to accelerate or not, right? That's just regular inertia. Rotational inertia, I, is describing how much does this thing like to rotate. And so it really depends on two things, okay? It's not just the mass. It's also where the mass is located compared to the axis of rotation. And so the idea is that if you have mass nice and close to the axis of rotation, this thing is going to be easier to rotate. And so the picture they give you in this little short section is that if you're spinning something like this pencil along the axis down its center, all of its mass is really close to that axis. Okay, that's nice, very easy. If though you pick a different axis of rotation and you rotate it like along this axis, that takes more effort, okay, to do this than to do this. So we're going to be talking more about that. Sometimes the exam has some calculus that you could calculate these rotational inertias, but they also will sometimes give you the formulas, and that's what the next section is going to be about. Okay,